All right, let's talk about a problem that can drive any data scientist crazy. You've got dozens, maybe hundreds of time series variables, and they're all tangled together. Think economic data, sales figures, you name it. How do you even start to make sense of that mess? Well, it turns out there's a really elegant solution from Professor Kenichi Satoh's research, and we're going to break down exactly how it brings clarity to that chaos.
So here's the plan. First, we'll really nail down the challenge we're up against. Then, we'll look at two key tools in our toolkit, the good old VAR model and the super useful NMF. After that, we'll see the magic happen, how they're combined into something new, the NMF VAR model. And finally, we'll see it in action with a really cool case study.
All right, first up, let's get right into the heart of the problem. So here's the big question, right? You've got this massive web of time series data. Think about tracking something like the spread of a virus across, say, 47 different regions, or maybe you're looking at economic indicators for every state. Everything affects everything else. It's a mess. How on earth do you build a model for that without completely losing your mind in the complexity?
And this is where a lot of traditional models just fall apart. The more variables you throw at them, the more bloated and complicated they get. You might even get a model with a great R-squared, but it's a total black box. You can't explain why it's making the predictions it is, which, let's be honest, makes it pretty useless in the real world.
Okay, so to get to this new solution, we first have to talk about one of the classic go-tos for this kind of problem. I'm talking about the vector autoregression model, or VAR for short. The idea behind a VAR model is actually pretty intuitive, and honestly quite powerful. It basically says, hey, everything is connected. So what happens with variable A today doesn't just depend on what A did yesterday. Nope. It also depends on what variables B, C, and all the others were doing. It's fantastic for capturing how all these different threads influence each other over time.
But, and this is a huge but, that very strength is also its fatal flaw. Every time you add another variable, the number of parameters the model has to estimate doesn't just go up, it explodes. This is what we call the curse of dimensionality, and it hits VAR models hard.
Okay, so how bad can it get? Let's take the exact data set from the paper we're looking at. COVID-19 cases across 47 prefectures in Japan, using just the past 7 days to predict the next. How many parameters do you think a standard VAR model would need for that? A few hundred? Maybe 1,000? Nope. The answer is 15,510. It's just insane. A model with that many moving parts is not only a nightmare to train, it's almost guaranteed to overfit and be incredibly unstable.
So if a standard VAR model blows up like that, what do? We need a way to simplify things, to find the underlying structure. And that brings us to our second key ingredient, non-negative matrix factorization, or NMF.
So what is NMF? I love this analogy. Think of NMF like a chef breaking down a complex sauce. It takes your data and figures out the fundamental ingredients. These are your core patterns. That's one matrix. Then it gives you a recipe for each data point, telling you exactly how much of each ingredient went into it. That's the second matrix. So you're not looking at the final complex sauce anymore. You're looking at the simple components that make it up. And this has some really cool advantages. First, because everything has to be non-negative, you can't have a negative amount of an ingredient, right? The parts it finds are actually interpretable and additive. But the real game changer for me is what's called soft clustering. This means a data point doesn't have to belong to just one group. It can be, say, 70% group A and 30% group B. That's so much more realistic than forcing everything into a single box. Okay, quick recap. We have VAR, which is great at modeling how things change over time, but gets way too complex. And we have NMF, which is amazing at finding simple underlying parts. So the million-dollar question is, how does Professor Satoh's research put these two powerful ideas together? And this is where things get really, really smart. The big idea isn't to just use NMF to pre-process the data and then run a VAR model on the smaller data set. No, that's the obvious way. The truly brilliant move here is to build the NMF structure inside the VAR model's coefficients. You're basically forcing that huge, scary matrix of 15,000 parameters to have a simple, low-dimensional structure from the get-go.
So here's the flow. The model starts by assuming that what we see today is really just a combination of a few core latent patterns. Let's call these the fundamental ways a virus can spread. Then it figures out today's specific mix of those patterns based on what we saw happening yesterday, the day before, and so on. So what you end up with is a VAR model, but instead of having thousands of independent coefficients, they are all neatly defined by that small set of core patterns. It's like it simplifies the whole system from the inside out.
And the paper itself says it best. This expresses the VAR coefficients in a low-dimensional form via the basis matrix X. That's the whole magic trick right there. You're not losing the power of the VAR framework. You're just making it smarter and more structured, which is exactly how you beat that curse of dimensionality.
Okay, this all sounds great in theory, right? But does it actually work? Let's dive into that real-world COVID-19 dataset from Japan and see what this NMF VAR model can do.
So remember that absolutely wild number from before? 15,510 parameters for a standard VAR? Well, check this out. The NMF VAR model? It needed just over 1,500. That is a 90% reduction in parameters. That's not just a small improvement. That's a whole different ballgame. That right there is the power of this approach in a nutshell.
And you might be thinking, okay, you made it simpler, but did it ruin the performance? Not at all. The model still got an amazing fit, an R-squared of 0.97, and it was stable. But here's the part that is just so cool. The model was given zero geographical information. It didn't know which prefectures were next to each other, and yet, just by looking at the infection data, it automatically discovered 4 distinct, geographically meaningful regions. It found the hidden structure all on its own.
And this is a perfect example of that soft clustering we talked about earlier. Take Ibaraki Prefecture, for example. The model says its infection pattern is about 90% explained by the dynamics of Region 1, but it's not 100%. It also has these little bits of influence from the other regions. This is so much more powerful than just saying Ibaraki is in Region 1. It captures the nuance of how these areas are interconnected in reality.
And it gets even better, because the model doesn't just find static groups, it shows us how their influence changed over time. You can literally watch the story of the pandemic unfold. Early on, it was dominated by the pattern from major urban centers. Then the center of gravity shifted to other populous coastal areas. And later still, the dynamics in western and northern Japan became more important. The model tells this whole dynamic story completely on its own, just from the numbers.
So, let's zoom out. What's the big takeaway here? This NMF VR model isn't just some obscure academic exercise. It's a genuinely powerful and practical tool that you should seriously consider adding to your own data science toolkit.
Now let's be real, there's always a trade-off. And you can see here, the standard VAR model can eke out a slightly higher R-squared value. It gets a 0.999 versus a 0.970. But let's really think about what that means. You're sacrificing a tiny, tiny fraction of predictive accuracy for a model that is 90% less complex, way more stable, and most importantly, actually interpretable. I don't know about you, but in any real-world project, that is a trade I would take every single day of the week.
So, to wrap it all up, what NMF VR gives us is this incredible framework. It successfully tames that curse of dimensionality. It lets us discover these hidden interpretable patterns. It allows for dynamic soft clustering. And it does all of this while making our models more stable and scalable. It's not about ignoring the complexity, it's about finding the elegant simplicity hidden inside it.
And that really just leaves one final thought. We've talked about a pandemic, but what about other complex systems? Think about the stock market, with hundreds of interconnected assets, or customer behavior across a huge product catalog, or even the firing patterns of neurons in the brain. What massive, tangled-up data set are you working on that might finally reveal its secrets if you looked at it with a tool like this?